we're the Drone Automated Mesh Network. Let's look at a problem. Drones are becoming incredibly capable and important tools in society, but they're limited by one major factor: their range. What we can't do is simply add more batteries, because as we add more batteries, we add more weight, which has diminishing returns in terms of range. It would be extremely valuable to indefinitely extend the effective range of our drones. We just have to come up with a solution. Our goal over the last year is to develop a solution to that problem. We wanted to create a proof of concept for that solution, and we want to assemble a prototype of that proof of concept. Here's our design. We wanted to create a wireless charger capable of being mounted on any drone. We wanted to charge that drone with a permanent platform infrastructure that's going to be self-powered, so you can place it anywhere in the environment that's needed. For our project, we chose solar. We've also developed a wireless communication system to help connect a collection of drones and platforms into a wider network capable of large-scale computing and coordination.
Our implement solution is much simpler and aims to provide a proof of concept to our design ideas. For our wireless charging, we are using commercial off-the-shelf Qi charger coils at 5 volts and a basic platform to hold our platform components and power transmission coil in place, as can be seen in the top right corner. A simple point-to-point wireless communication network is implemented using our XB's DigiMesh protocol to communicate things such as battery levels, position, health, and statuses between the platform and the drone.
The design specifications we worked towards was obviously making sure the drone battery was able to charge wirelessly from the charging platform. We also wanted to provide a 12-charge platform battery capacity while running the system off of solar power, as well as designing the platform to be lightweight with a dynamic landing zone.
So we wanted to get about 5 watts being transmitted wirelessly in order to charge the 500 milliamp hour drone battery in about 20 minutes. Using that number, we sized the platform battery to be 7 amp hours so that we could have a good number of individual charges, just in case we didn't have enough sunlight for an extended period of time. This came out to be about 12 charges at minimum. And as far as the switching frequency goes, we chose to use 120 kilohertz throughout the project to make things easier on us to make sure we're using the same frequency everywhere. And we assumed the coils would be about 4 to 7 centimeters apart when sitting on the platform. We used those numbers for our coil calculations.
Here we have our system diagram slide. We'll start with the platform side. Our solar panel is used to charge our 12 volt 7 amp hour platform battery. This voltage is stepped down to 5 volts by our buck boost converter, which is then used to power our microcontroller, our GPS module, and our XB. Power from the battery is passed through a MOSFET gate driver and an N-channel power MOSFETs before going through the coils and being transferred to the drone side. Once on the drone side, power is transferred through a full bridge rectifier so it can be used to charge our 3.7 volt 500 milliamp hour LiPo battery. Power from the drone battery is stepped up to 5 volts in order for it to power our microcontroller, GPS, and XB on the drone side.
The first thing that we had to figure out was how to power this whole thing. We wanted to make sure the platform was completely self-contained wherever we decided to put it, just in case it's out in the middle of nowhere, so no one would have to maintenance it for a while. So we decided to go with solar. It seemed to be the right fit. We decided on a 40 watt solar panel, and we fed it into a charge controller in order to normalize the voltage and current output, regardless of the time of day, to circumvent the changes in cloud cover, etc., anything that might make the outputs fluctuate. And then using this controller, that would feed into the sealed lead acid battery within the platform, which then would feed the entirety of the rest of the project.
From the solar panel source, we needed to consider how the power was going to be managed throughout the system. We designed an H-bridge inverter to convert the DC signal coming from the solar panel into an AC signal for the coils to wirelessly transmit. From the simulations, we were able to measure a square wave signal of 24 volts peak to peak and 4 amps peak to peak. We also used the MIC 4606 gate drivers to control switching the MOSFETs on and off. We use IRF 540 MOSFETs on the H-bridge since they fit the requirements for fast switching capabilities.
On the drone side, we needed to rectify the AC signal back to DC to provide appropriate power to the battery charger and microcontroller. To achieve this, we designed a full-wave bridge rectifier, which gave us a 7.7 DC voltage and 1.5 amp signal. We also included the linear regulator as an option to help us regulate the power from the rectifier. Additionally, battery chargers as well as DC converters were utilized to manage system power.
In order to wirelessly transfer power, we're using two single coil designs with the expectation to transfer about 5 watts. In order to make the two coils resonate at our desired frequency of 120 kHz, we're using two capacitors in series topology, which ensures we are efficient in our transfer of power. The coils are made from a braid of extremely thin wires called Litz wire to minimize the skin depth effect, allowing more current to be supported in a smaller footprint. ANSYS Maxwell was the tool of choice to model the electrostatic interactions between our two coils and provides the self and mutual inductance of the coils to determine our power transfer efficiency.
For our project, we had a set of goals that we wanted our microcontroller to accomplish. In order to achieve these goals, we went with the Atmega Explain Mini with the Atmega 328PB processor. We utilized the two UART interfaces to communicate between our GPS and RF modules. We used the microcontroller to generate PWMs for the inverter, as well as the multiple analog to digital converters to monitor different voltages such as battery power. In comparison to other development boards such as Arduino, the Explain Mini allowed us to use extra debugging features provided by the IDE, as well as create a cost-efficient option for our project. The data that we had to communicate between the drone and platforms were GPS data such as longitude, latitude, and GPS status, and the systems data such as battery level and a signal to enable charging. To accomplish wireless communication, we went with the XB RF module for its multi-point digi-mesh network and power efficiency. Another factor was range. For our demo, we went with a less powerful transceiver for cost efficiency. However, it can be upgraded to a much longer range without a large fluctuation in price. Another reason we went with the XB was for its powerful yet user-friendly configuration and test utility. It allowed easy configuration of the wireless network as well as access to hardware and software features on the module. It also provided extra testing tools such as the serial console as seen on the slide. This allowed us to test the modules at the same time to confirm that they were set up correctly before interfacing with the microcontrollers.
To provide navigational info for our system, we decided on the Adafruit Ultimate GPS. It operates at 5 volts 20 milliamps. It comes with an internal antenna and provides less than 3 meter accuracy, which makes it perfect for our project. Having to operate at 5 volts 20 milliamps and coming with an internal antenna makes it very easy for us to wire it up to our microcontroller and immediately begin receiving data from it. We wanted to extract the latitude and longitude to prove the first steps in having a drone autonomously land on the platform and begin charging without human interference.
We'd like to thank our faculty advisor, Professor Chris Mee, and our industry advisor, Andrew Bushnell. For more information, such as our schematics and poster, please visit our website and feel free to email us for any questions.